During this lecture, we will summarize what you should already know about the soil state, and then I will just add a few words about the colloidal activity of soils. If you wanted to describe a soil, the first thing that you would mention would be the grain size distribution. So the proportion of the particular fractions of the soil to the whole soil mass. This can be determined with the use of direct or indirect methods. One of the most popular direct method of the grain size distribution determination is the sieve analysis. Actually, here we are not measuring the real size of each particle or each grain. We are just checking what part of the sample is passing through sieves of specific sizes or specific diameters. You could also try to use microscopic analysis to determine the grain size distribution. However, it is not really done so. The microscopic analysis can be rather used to determine the shape of the particles, not their size. If the soil particles are too small to use the sieve analysis, by too small, I mean smaller than 0.063 millimeters. In such a case, we need to use some indirect methods of the grading analysis. One of the examples is a hydrometer analysis. In all these methods, we are substituting the particle size by diameter of some sphere. In the hydrometer analysis, we are using a tool looking basically like this, so of such a torpedo shape, and we are introducing that into a soil water solution, which is poured into a glass cylinder. When the hydrometer is entering this mixture, it is measuring the bulk density of this mixture, and this bulk density will be decreasing with time while the solid particles are sedimenting in this solution. If we already know the grain size distribution of the soil, which requires, for instance, the sieve analysis and hydrometer analysis if the soil is a mixture of coarser and finer particles, then we can usually give a name to the soil. So we can, for instance, call it clayey sand or silty clay and so on. But the name of the soil and the soil grading is not always enough. The other thing which is really important if you are describing a soil is the soil state. Now, if we are talking about the coarse soils, so sands, gravels, and so on, then the soil state is best described by the state of compaction of this soil. And the parameter that we are using here is the density index ID. Sometimes we call it relative density. So in the literature, you can find both expressions. The density index is the ratio between the density of soil in its natural state to its highest possible density. It is determined for coarse soils only, as I said, because here the arrangement of grains influences the soil properties and the soil behavior. The ID can be defined either using the total volumes of the sample or using just the volume of voids of the sample or using the void ratios. Because we are assuming that the volume of the skeleton, as you can see, is not changing because we are assuming that the skeleton is incompressible. So what can be changed in the soil sample refers only to the voids. That's why we can calculate ID using either the total volume or the volume of the voids or the void ratios. And in the definition, always here in the top of the comparison, you will have the maximum void ratio minus the current void ratio of the sample divided by the range of the void ratios, so the Emax minus Emin. To determine the index of density of sand or gravel, you need to know the current void ratio of the soil and the possible maximum and minimum void ratio. The current void ratio is quite easy to be determined if you know the water content of the soil, its saturation, and the relative gravity. Then you simply using the equation that you learned during the lecture number 2, you can calculate the void ratio. But what about the maximum and minimum void ratio? To determine them, you would need to know the particle density of the soil and, for instance, the dry density of the soil. And for the maximum void ratio, we would have to know the value of the minimum dry density of the soil, and for the E-min, we would have to know the ρD max. Now, how to determine these two dry densities? Well, there are various methods that can be used here, various laboratory methods. It depends on the standard. For instance, in the old Polish standard, we were using this set of tools, which is presented here on the left. So we would have a cylinder like that, would have such a top cap with a hook, and we would have such a tool that looks like a fork, let's say. To determine the loosest possible state of the soil, so that is referring to the Emax, okay? In the loosest possible state, you can determine the minimum dry density of the soil if you know the water content of the soil and its bulk density in such a state. So to create such a state for sand, we would simply pour the sand into the cylinder using kind of a funnel. So the bottom of the funnel would be placed at the bottom of the cylinder, and the sand would be poured using the funnel, and the funnel would be then lifted very, very slowly and carefully upwards until the whole cylinder is filled with the sand. Then, of course, if you cut if you level the top of the specimen and measure the mass of the cylinder with the soil, then you can calculate what is the mass of the sand in the cylinder. Knowing that, and knowing the water content of your sample and the mass of the cylinder alone, you can easily calculate the dry density of the soil in this loosest state. Now, to get the most compacted state, the densest state of the same sample, we would use this fork. So we would place this top cap on the top of the specimen, and then by means of this fork, by hitting the cylinder with it, we would create some vibrations that would result in compacting the soil sample. And of course, the top cap, which was placed here, would then slowly enter into the sample. If after several minutes of this activity, we wouldn't notice any more movements of this top cap, we could assume that the soil is in its densest state. So that is the old Polish standard. In American standards, for instance, we are using the cylinders which are similar to the cylinders for the Proctor test. To determine the maximum void ratio, the method is very similar. I mean, you simply have to obtain the loosest possible state of the soil. So usually people use the funnel to create the sample. But to obtain the densest state, in many standards, it is required to put the cylinder filled with the soil on a vibrating table, and this vibrating table then is applying the vibrations that compact the soil. And this method probably is much more effective than this manual method that was described in the old Polish standard. The density index ID is used to classify soils based on their density. And again, this classification depends on what standard you're using. Right now, based on the European standard, we are having 5 different states: very loose, loose, medium dense, dense, or very dense. And the limits are presented here. You can compare these limits with, for instance, the old Polish standard, which is shown here. So in the old Polish documentation, or the current documentation, but based on the old Polish standards, you would see that the ID was then expressed as a ratio. Right now it shall be expressed in percent. We wouldn't have a very loose state, but we would start with the loose state. And the limits were, as you can see, slightly different. Now, why do we compact the soil? Why do we want it to be dense? What do you think? Well, first of all, we want to decrease its void ratio, and so also its permeability. Secondly, to increase its shearing strength, and so its bearing capacity. And also to decrease the soil sensitivity to future volume changes. So, for instance, the settlement due to loading and vibration. The effectiveness of compaction depends on several factors. First of all, it depends on the soil type and its current state. Because some soils will compact more, some soils will compact less. It depends, of course, on the maximum and minimum possible void ratio of the soil. It depends also on the natural water content of the soil. If we were talking about cohesive soils, then the state naturally depends on the water content. But if you are talking about coarse, so non-cohesive soils, then you already also know from the Proctor compaction test then that the dry density depends on the water content. So it depends on the ID parameter. As I mentioned before, the effectiveness depends, of course, on the maximum and minimum state of compaction, because if your soil is already quite well compacted, then you cannot increase its density much more, right? It depends, of course, also on the compaction technology and on the equipment used. For instance, if all what you had was just a herd of cows and you were to densify, to compact some sand on a field, then using this herd of cows, you would compact it, of course. But the extent of this compaction would be much smaller if you were using much more professional equipment, right? To check the ability of soil to compact, we are looking at the dry density. It is the best parameter to describe the effectiveness of compaction, for instance. And most of the soils will behave like shown here. So depending on the water content, the dry density will be different. And there would exist some water content for which we would be able to obtain the maximum dry density. This water content is called the optimum water content. Why it is happening so? That initially the increase of the water content is resulting in the increase of the dry density. But from some point on, the further increase of the water content will lead to the decrease of the dry density. The explanation is given here. So when the water is added to the soil, on the solid particles, a layer of absorption water is created. As the water layer increases its thickness, the soil particles become to be able to move relatively to each other and fill the empty spaces, resulting in the increase of the density. So water is initially acting as a lubricant, let's say, right? But if there is too much water, then the pressure of the water is pushing the soil grains away, resulting in the decrease of the density. So here it is the action of the pressure pushing the grains apart. That's why we observe the decrease of the dry density. This refers only to the soils which are not self-draining soils. The optimum water content and the corresponding maximum dry density depend on the energy of compaction. That means that if you are using bigger runner, or if you are dropping it from higher, from bigger height, or if you are compacting the soil in more layers, or if you are applying more blows on each of the layers, then the energy of the compaction will be greater. and so the maximum dry density will possibly be also greater. You would notice that with the higher energy of compaction, you can get a higher maximum dry density, but smaller optimum water content. This results from the fact that in this space, rho dW, there exists a boundary. This is the zero air voids line. So if all the voids of the soil are already filled with water, then you cannot move any more further towards right, so you cannot increase the water content. That's why we observe here this boundary. So the grading curve can only like slide along that boundary. The optimum water content and the maximum dry density are very important parameters of soil because they let us know at what water content we shall compact our soil while, for instance, building an embankment. To check these values in a laboratory, we have to use some standard method. And the engineers all over the world have decided to follow the proposal of Ralph Proctor. He was an engineer who, in 1933, has discovered this fact that the dry density depends on the water content of the sample when it's compacted. So to honor his experiments, we are calling the standard compaction test a Proctor test. Taking into account the fact that the different energy of compaction will give you different results, the standards in many countries will suggest various methods of soil compaction. For instance, if you looked into the Old Polish standard, you would find 4 methods of soil preparation in the Proctor test. The first 2 would be simply called Proctor tests, while the third and the fourth would be called a modified Proctor test. What is the difference between them? So the first, during the first 2, so if the first 2 methods are applied, the soil is compacted with the energy equal 0.59 joules per cubic centimeter. To obtain this energy, we are using 3 layers of soil which are compacted with 25 blows if a small cylinder is used, or 55 blows if a bigger cylinder is used. And we are using hammer with the weight of 2.5 kilograms, and it falls from the height of 320 centimeters. If we want to apply higher energy, then we would use the modified Proctor method. So this is the method 3 and 4, where the energy equal to 2.68 joules per cubic centimeter is applied. As you can see, the difference between the first 2 methods and the second 2 methods is the number of layers and the height of the cylinder and the height of the drop. When we want to use the European standard for the Proctor test, we can choose out of 6 methods. Again, 3 of these are the Proctor test, and the other three are modified Proctor test. Again, the energy is different in the Proctor test and in the modified Proctor test, but if you compare them with the energies used in the according to the Polish standard, you would see that they are basically the same. This additional third type of the test is the test conducted in the mold C, and this is a very big mold which is used for the coarsest materials. The results of the Proctor test, so the optimum water content and the maximum dry density, are used in practice when road embankments are being built. First of all, the optimum water content is used to prepare the soil for each embankment layer, because we would now know how much water we shall add to the soil to obtain the best effectiveness of compaction. The maximum dry density is also used to check the effectiveness of the compaction by means of the parameter called coefficient of compaction IS. The value of the coefficient, the required value of the coefficient, is usually given in some regulations for building the specific structures. For instance, in this standard, you will find the picture as shown here, where the required values of the IS are given, as you can see. Okay, what is that IS? IS is a ratio of the dry density of soil in situ conditions compared to the maximum dry density obtained in the laboratory in the Proctor test. So as you can see, the required values of IS are very close to 1. But for some structures, for instance for highways, sometimes it is even required to have the IS value greater than 1, which would mean that it is required for the embankment layer to have the dry density in field, so in the embankment, higher than the maximum possible one that was obtained in the lab. In some books, you can find the empirical formula for the coefficient of compaction. It's given here, which means that if you know the index of density, then you can also assess the value of the coefficient of compaction. So to calculate the value of the coefficient of compaction, you need two pieces of information. First is the dry density of the soil layer in situ, and the second is the maximum dry density of the same soil compacted in the Proctor test. How to conduct the Proctor test, you know perfectly well because you have done it personally. But how to determine the dry density in field? Well, here again we can use this formula. So if we know the bulk density of the soil and its water content, we can calculate the dry density. Let's first start with the water content. You know how to calculate or how to determine the water content using laboratory equipment. You simply have to take a soil specimen measure its mass, and put it into the oven and measure the mass after drying. Using these values, you can easily calculate the water content. The problem is that this method requires time, and time is money. So it would be very useful if we had some other method of determination of the water content. And of course, there are such methods. For instance, you can use an apparatus called a nuclear gauge. It looks like that. First, you locate a template in the specific place where the water content is to be determined. My colleague from Porto is showing that to you. Of course, she's showing that in the on the floor. That should be done in field, but well, this is where she was able to show that to me and to you. Okay, so first you locate a template, and then in the same place you put the equipment. And you can simply read the value of the water content from the screen. So the method is really fast. If we already know the water content of the soil layer, then what is left to be determined is the bulk density. Bulk density, so the mass of the sample and the volume of the sample. So of course we can dig a hole, right, and take the sample from the hole and measure its mass. It is not a problem. The problem is how to determine the volume of that sample, because if you take it to some plastic bag, then of course the volume of it is different than the volume of the soil in the ground. So you would have to measure the volume of the hole that you have created. The easiest method to do that, if you really do have no equipment, would be to cover the hole with some plastic bag and fill it with water. Right? If you know the volume of the water that you poured into this hole, you would know what is the volume of the hole. But you can also, of course, use some more sophisticated equipment, like the one presented here. This is called volume sand density cone apparatus, and looks like that very simply. So we have some standard cone and a container with some sand of the standard parameters. So we put that cone, we locate the cone over the hole that we have created, and we have the standard sand in the container. We weigh the sand before the test. Then we open the valve here. The sand is entering through the cone to the hole, and then we can weigh the container with the sand after the test. The difference will give you the amount of soil that is filling this volume. Of course, the volume of the cone is known, so when you subtract it, you will obtain the volume of the hole. And then you can calculate the bulk density of the specimen. You know already that the physical state of sands and gravels is best described with their density, while in silts and clays, it is the water content that has the most important influence on the engineering properties. We distinguish four physical states, or in other words, four different consistencies of silts and clays. These are the liquid consistency, plastic, semi-plastic solid, and solid. In some books you will not find this third one, so the semi-plastic solid, but in some you will. So the liquid consistency means that the soil behaves like a liquid and has almost no shear strength. The plastic consistency means that the soil deforms when an external pressure is applied, it doesn't crack, and keeps the shape. The semi-plastic solid consistency means that the soil deforms when an external pressure of higher value is applied, it cracks, and its volume decreases when dried. And the last, solid consistency, means that the soil deforms only at the very high values of external pressure, it cracks and does not change its volume when dried anymore. The boundaries between these consistencies are called Atterberg limits, and the boundaries are simply some specific values of the water contents, and these are the liquid limit WL, the plastic limit WP, and the shrinkage limit WS. The values of these limits may be estimated in laboratory tests. You should remember, however, that the values of the Atterberg limits are not some precise soil parameters. They're just some estimations. Let's see what is happening to a clay sample when it's being dried. So this point has got the coordinates Wn, E. Wn is the natural water content, and E is the current void ratio. On the vertical axis, we could show here either the void ratio or the bulk volume of the sample, because they are interrelated. So we are starting at this point. So the specimen is having very high value of the water content, and it's showing liquid behavior. The sample is, of course, fully saturated, so all the voids are filled with water. Now, if we start to dry the sample, then of course the water content will decrease, and the void ratio, or the bulk volume of the sample, will also decrease, but it will follow this path, just as you have seen it now. What we shall notice. Initially, the soil, if it's fully saturated, it is behaving linearly. I mean, in terms of the change of the void ratio against the water content. The inclination of this line will be equal to the specific gravity. It comes from this equation. Because for a fully saturated soil, the ratio of the void ratio and the water content equals the specific gravity value. If the soil stops being fully saturated from some point on, okay, so let's assume that from this value of the water content, the soil is no longer fully saturated. Okay, so our saturation ratio will become smaller than 100%, we'll observe that the volume of the specimen or its void ratio will stop changing. The soil then will be in the solid consistency, and there is no more water in the sample, only at this point. Between that point and that point, there is still some water in the pore voids, but they are not filling the voids completely because sample is not fully saturated, and their further decrease is not influencing the total volume of the sample. The liquid limit of soil can be determined with the use of various apparatuses and various methods. For instance, with the use of the Casagrande apparatus or the cone penetrometer. You know the procedures quite well already because they are available in the standards. There is also a third method with the use of the Vasiliev apparatus. It is quite similar to the cone penetrometer method because we are using a standard cone of the specified weight, and with this a kind of a balance on it. And the liquid limit is the water content of the soil paste, for which this cone is entering the soil paste by 10 millimeters within 5 seconds. No matter what standard you're using, the plastic limit is usually determined by the thread rolling method. So during this test, of course, we are preparing a ball from the soil sample, and then we are forming a thread. Just the details of the methods are different depending on the standard. What is quite interesting is this behavior of the thread that can be used not only to determine the plastic limit, but also to determine the soil type. For instance, this behavior is typical for silts, while this behavior with the perpendicular cracks is typical for clays. To determine the shrinkage limit of soil, you have to control the volume of the sample and its water content. So, for instance, we can put the specimen into a container of the known volume and of some regular shape. The volume of the sample then is expressed as VI, and the mass of the initial mass of the sample is M1. Then we put the sample into the oven, and we are gradually drying it. And in the meantime, we are checking how the volume and how the mass are changing during this process. To calculate the shrinkage limit, we can use this formula. So first, we will check how much the mass has decreased, and we compare it to the mass of the dried sample, and then we subtract this part where we have the difference in the volumes of the specimen before drying and after drying compared to the mass of the dried sample and multiplied by the density of water. You can also try to estimate the value of the shrinkage limit using this empirical formula. But as almost every empirical formulae, you have to be careful while using this equation, because it is not necessarily true for all types of soils. If we already know the values of the Atterberg limits, we can calculate three important parameters of state of fine soils, which are the plasticity index, IP, which is simply the difference between the liquid limit and the plastic limit. The second parameter is the liquidity index, which is the difference between the natural water content and the plastic limit compared to the plasticity index. And the consistency index is very similar to liquidity index. Actually, if you know the liquidity index, you can calculate the consistency index using this formula, so 1 minus IL. You can also try to assess the value of the liquidity index if you have conducted the thread rolling test, because this is an empirical formula again. So if you know the number of the successful thread rollings for your sample X, and if you know the content of the clay fraction and activity of your soil, then using this formula you can assess liquidity index. The liquidity index IL and the consistency index IC are used to classify the cohesive, so the fine soils, based on their physical state. And depending on the standard, these classifications can be very different. I would like to start this description with the Old Polish standard PN 86, because this standard was giving a very precise and sensible names of the soil states and soil consistencies. Let's look then at this part of the table. So, what can we read from this table? If the soil is between the, if the water content of the soil is higher than the liquid limit, then the soil is in the liquid consistency and liquid state. If the soil has got the water content between the plastic limit and the liquid limit, then the consistency of the soil is plastic, and the state can be either hard plastic, or soft plastic. Which one it is, it depends on the value of the IL, so the liquidity index. And actually, you can say that the range between the plastic limit and the liquid limit, which are exactly here. So here at this value, we have the plastic limit, while here we have the liquid limit, right? So if the water content is somewhere in between these two values, the soil is in plastic consistency. If we divide this range into 4 equal sections, then the hard plastic state takes like 1/4 of this section, plastic takes another 1/4 of the section, and soft plastic takes so half of the section. So if the water content of the soil corresponds to the value of the liquidity index between 0 and 0.25, the soil is in plastic consistency and hard plastic state. If the IL is between 0.25 and 0.5, the soil is in the plastic consistency and plastic state. If the water content corresponds to the IL value between 0.5 and 1, the soil is in the soft plastic state and plastic consistencies. So everything is nice and clear, right? But if you now look at the European standard, PN 14688, we will notice that the plastic limit, well, it is staying at the boundary between very stiff and stiff consistency, but the liquid limit, which should be somewhere here, doesn't have really any meaning. So it is very important to always mark clearly based on which standard you are naming your soil in terms of its consistency and state. The liquidity index IL and the consistency index IC, they depend on the current water content of the sample. So if the water content is changing, also the IL and IC values are changing. IP parameters of the plasticity index, it is a constant for a particular soil. It describes what percentage of water relative to the mass of solids a soil shall absorb to change its consistency from semi-solid to liquid. Highly active sodium bentonite, absorbing huge amounts of water, may have the IP value greater than 200%, and little active lasses, like port silt, they can have the IP value of only 5 to 10%. So the plasticity index depends very strongly on the mineral composition of soil. Soils with small plasticity index may liquefy even at very small water content increase, because it is not much water content change necessary to dramatically change the soil consistency. In the table on the right, you can see the typical values of the liquidity, the liquid limit, plastic limit, and the plasticity index, and the shrinkage limit of soils built of various clayey minerals. So you can see that the Montmorillonitic clays will always have very high values of the liquid limit, while the kaolinitic clays will have these values even 10 times lower. As you hopefully remember from the previous semester, the results of the Atterberg limits can be used to classify defined soils. So here we are using the Casagrande plasticity chart, which depends on the liquid limit and the index of plasticity. All defined soils can be shown on this graph by a point of some specific coordinates of the WL and IP. So if this coordinate falls below the A line, then the soil can be named sealed, SI. Depending on the value of the liquid limit, it will be a sealed with low liquid limit, medium liquid limit, high liquid limit, or very high liquid limit. If the coordinate of the soil falls above the A line, the soil shall be called clay. Okay, and again, with the second letter would be L, M, H, or V, depending on the value of the liquid limit. The ratio of the plasticity index and the content of the clay fraction is called the activity of soil. Sometimes we call it colloidal activity of soil. Most Polish soils are characterized with the activity equal to 1. That is why the clay fraction content and the plasticity index value used to be the basis of the soil classification in the Polish standard. Because if you knew the value of the IP, then you could assume that the value of the clay fraction content would be similar. Right now, we know that there are some exceptions and not all soils behave like that. If the soil activity equals 1, that means that the clay fraction against the plasticity index would be placed along this red line. And as you can see, most of the soils are following this shape. So they're close to this red line. But there are some exceptions, like montmorillonite clays, which will have the plasticity index much higher than expected. We say that these soils are very active, and they will also be characterized with high expansive properties. On the other hand, we may find lasses and weathering clays, which will have the plasticity index lower than expected. All that so depends on the mineral composition of the soil. You can see that in the table on the left. So for instance, eolite, which is very typical clay mineral, will have the activity equal to 0.9. But the montmorillonite will have the activity higher than 1.25. If this is a sodium montmorillonite, the activity can be really huge, of around 7 even. Still, most soils in UK or Poland or Europe generally will have the activity from around 0.75 to 1.25.